Hi everyone, welcome back to PW International Boards. Friends, in this class, we are going to talk about another chapter for our Physics Cambridge IGCSE exam. And this chapter is thermal properties and temperature. First, we are going to talk about all the theoretical concepts. Then we are going to also solve some of the past question from this particular chapter, right? So without any delay, let's first talk about what are going to be the topics that we are going to cover in this class. We are going to talk about thermal expansion, uses of expansion, specific heat and change of state, right? So let's start today's class and let's discuss what do we really mean by thermal expansion. If you remember from the last class, we said that if you are going to actually heat a body, because of this heat, the particles which are in the body are going to actually move apart. So particles will move apart from each other because of this thermal energy, right? Now we are saying that when matter undergoes heating without transition into the different states. So right now we are not talking about that the state is going to change. It typically experiences expansion. This is what is known as thermal expansion. So we are going to consider following cases. Let's suppose that we have got a rod, and rod is something like this. I have deliberately assumed that the rod has got no thickness, right? I know that it doesn't sound practically possible. Obviously, it's not practically possible to have a rod which has got no dimension, which has got no width. But right now we are talking about a theoretical concept. We are saying that let's assume that we have got a rod which has got length L and it has got only one dimension, which is this length, right? And right now it is at, let's say it is at temperature T. And if you are going to change the temperature, let's suppose the change in temperature is actually del T. So what we are saying is now the length of this rod will change, and let's say this is the change in length. This amount of length is actually the change in length, which will be written as delta L. This type of expansion is known as linear expansion. All right. This is because of heat. So let's suppose that now we have got a two-dimensional surface, something like this. Now, if you are going to say that initially it is at temperature T and now we have increased its temperature by del T, that is a small change in temperature. Now we are going to say that the length of all the four edges will actually increase. So the new shape would look something like this. This is called as aerial expansion or superficial expansion or surface expansion. We can also call it as surface expansion, not superficial, surface expansion or aerial expansion. Similarly, if you are going to talk about a three-dimensional body, that type of expansion will be known as a volumetric expansion. Now we need to note few things over here. These types of expansion actually it directly depends on the change in temperature. It also depends upon, so this thing also, this expansion only, whether it is linear, aerial or volumetric, this depends upon the on the material of the body. So let's suppose I've got two bodies and I have placed them in the same environment and I have increased their temperature by the same amount, but one expands to a greater extent as compared to the other. So I'm going to say that this material is the material of the first body is actually something which responds to heat very easily or responds to heat more efficiently as compared to the another, right? So expansion will definitely depend on the material. It will also depend on the change in temperature. So more is the change in temperature, more is going to be the expansion. Well, that's the general case, right? We are going to talk about the exceptions also. Now, using the concepts of thermal expansion is very important in various places that we are going to talk about. So first let's discuss some things. Thermal expansion is minimum in case of solids but maximum in case of gases, because intermolecular forces are maximum in solids and minimum in gases. This comes from the knowledge that we have gained from the kinetic theory of gases. So this is nothing but this is actually not kinetic theory of gases, but it is just the this is just the kinetic theory of matter. Kinetic theory or particle theory of matter. So we know that the spaces between the gas is actually maximum, right? So that's why we are saying that this thermal expansion will be minimum in the case for solids and maximum in the case for gases, because intermolecular force is minimum in the gases, right? So this is very important. Solids can expand in one dimension, that is linear expansion. Two dimensions, well, you can use the word superficial because it is given in your textbook. And three dimension, that is volumetric expansion, while liquid and gases usually suffers the change in volume only. Please understand this point. If you are going to talk about a solid body, for a solid body, all the three types of expansion is possible. But if you're going to talk about a gaseous body, for a gaseous body, only volumetric expansion is possible for gaseous as well as liquids, right? This is very important. Now, what are the uses of expansion? This is actually something which is important for you, because you might be also knowing this, that this usually comes in your exams, right? So this thing is actually important. For the first one, we are talking about a bimetallic strip. Now, what really happens with a bimetallic strip? When we are going to talk about a bimetallic strip, we have got two strips which are joined together, and they are made up of different material like copper and iron. Now we are going to expose them to a change in temperature. Now what will happen? Copper and iron are obviously, they are different materials, so they will react differently to change in temperature. And the fact is that copper actually expands more. Copper expands more than iron. So this is a fact, and this will be also, actually it will be also defined by a temperature coefficient of different materials. Although that is not in the course, so we are not going to talk about temperature coefficient right now, because we are just discussing about the most important topics, right? But when we are going to learn about this chapter, I mean, with lots of time, we are going to talk about something that is called as temperature coefficient, right? So copper expands more than the iron. So what will happen? If copper expands more than the iron, it will actually try to bend the iron, something like this, right? So this is the case. Now let's suppose that if you have got two rods, and two rods are something like this, you have got one rod over here and you have got another rod over here, something like this. This is rod A and this is rod B. The rod will bend in that direction, which has got which is actually more, what we can say, which will actually expand more to the same change in temperature. So right now we are saying that copper is expanding more, so that's why it is actually bending the iron, right? So this is very important. We are going to use the bimetallic strip in many cases, right? And some of the first cases actually for an fire alarm. So how does a fire alarm works? The heat is emitted from the fire, causes the metallic strip to bend. So this will actually bend in somewhat in this direction. Somewhat in this direction. You know that below we have got copper. So it will bend in this direction. It will touch this contact point, right? As soon as it touches the contact point, this electric bulb will get activated. It will actually it will activate the electrical bell, and that's how the fire alarm basically works, right? So this is the first case, one of the most simple cases. Next, see, now there is one doubt for many students: why are you using a bimetallic strip? Why can't you just one single strip? The answer is, if you are going to actually, let's suppose, let me explain it over here. Let's suppose that they both are of same material. We are not using different materials. They both are of same material. So you know what will happen? The thing that will happen is, they both will actually expand linearly, something like this, in a straight path, and it won't bend. The idea behind the bending of a bimetallic strip is that one of the material expands more than the other. That's why it tries to bend the another metallic strip, right? So this is the idea behind it. If they both are of same material, it will just expand linearly. It's not going to bend. So we need to use actually bimetallic strip. Moving on, the next case for a bimetallic strip is, so first we talked about the uses of thermal expansion. In that we talked about bimetallic strip. Now we are talking about the uses of bimetallic strip, and in that one we have already discussed how a fire alarm works. Now we are talking about a thermostat. A thermostat is actually a device which actually maintains the temperature of any appliance, or it can maintain the temperature of a room as well, right? So how does it work? It works on the same phenomena. Let's suppose that we have got a heater over here. Let's suppose we have got a heater over here, and this heater is actually connected with this bimetallic strip, and there we have got a control knob. So now what's going to happen is that when the temperature will actually rise, this bimetallic strip will actually bend, and now this bimetallic strip will bend in this direction. So if it will bend something like this, the connection of the heater will be lost, and heater will actually stop, right? Because if it is bending, it basically means that the temperature is rising, right? So now the heater will stop working, and as soon as the temperature goes down, the rod will become straight, and again that heater will start. So that's how a thermostat works. A thermostat functions to maintain a consistent temperature within a room or an air or an appliance. The mechanism employs a bimetallic strip within the electrical heating circuit of devices such as an iron. Once the iron attains the desired temperature, the bimetallic strip bends downward, disrupting the circuit at the contacts and deactivating the heater, right? So that's how it works. Moving on, there is also very important use of thermal expansion as a precautionary step, and that is, we actually, whenever the railway tracks are actually laid down, there is sufficient amount of space between the tracks, and the reason is that during summers, summers, we expect that the iron rail track is going to expand, and we need to actually leave some space for that. Historically, that's what this point says. Historically, gaps were left between railway lines to accommodate expansion during the warmer seasons, resulting in the familiar click sound as trains transferred over them. So you know it, if you have ever traveled from a train, that we usually hear a periodic click sound, and this is the reason why we actually hear that, right? Moving on, if you remember, we talked about, when we were talking about thermal expansion at the start of our class, we said that generally this happens that whenever a particle, whenever a matter is heated, whenever an object is heated, it expands. But there is an exception. The exception is what we call as anomalous behavior of water, or anomalous expansion of water. This happens. Now I would like to read something for you. Substance typically expand when heated, leading to a decrease in density. Why is that? Why we are talking about that? For a very simple reason, that we know density is actually written as mass by volume, and if you are going to actually heat them, their volume is going to actually increase, and if their volume is going to increase, well, while heating, the mass will not actually change, right? Even if there is a change in state, we are going to assume that we are talking about an isolated system, and we are going to say that mass never changes. Let's not talk about all of those things, that if we boil some water, the mass of the water changes. Well, it does not. The mass of water it is just same. Now the state has changed from liquid state to now vapor state, right? So if the volume increases and mass remains constant, so the object becomes less and less dense, right, on expansion. But that's not what happens when water is cooled down till 4 degrees Celsius. So this basically means, if you are heating a matter, if you are heating an object and it is expanding, and we are saying that its density is going down, so this basically means we can also say that if we are going to cool down a body, its density will actually increase. But that's not what happens. What really happens with water is that its density actually decreases till 4 degrees Celsius. So there is something very, very important. a very important thing that happens at 4 degrees Celsius. After 4 degrees Celsius, when you actually decrease the temperature to, let's say, 0 degrees Celsius, the density does not decreases, right? The density actually does not increases. That's what we expect, right? If you are going to actually cool down a body, the density would increase, because if a very simple fact, if you are cooling a body, that would mean that the body would contract, and that would mean that the body will actually, the density will increase. A very simple thing. If you are going to heat a body, this would mean that a body will expand, and this would mean that the density of the body will go down. A very simple phenomena. But something different happens when you actually cool down water from 4 degrees Celsius to 0 degrees Celsius. Its density actually, which should go actually down, which should decrease theoretically, but that's not what happens. Its density actually decreases, right? And this is a very important phenomena, because of which actually marine life can sustain on Earth, right? We talked about this phenomena in the last class as well, but because we are now, right now in this chapter, we are talking about expansion, so this is again very, very important, right? So please note, we are going to also look for graph for this concept. Water exhibits a unique response to temperature changes. Until reaching 4 degrees Celsius, cold water follows the general trend without significant deviation, and this is what the general trend is that I have written over here, right? The next is, the density of water gradually increases as it cools, reaching maximum at 4 degrees Celsius, and then the density goes down. So till what we can say, till 4 degrees Celsius, its density is actually going down. Please try to read this graph. I'm going to help you out. Over here we have got volume, so we are not talking about density versus temperature graph, we are talking about volume versus temperature graph. So if volume is going down, it basically means density is going up. So if volume is going down, we can see that at 4 degrees Celsius, we have got the minimum volume. That means at 4 degrees Celsius, the water has the maximum density. What happens after 4 degrees Celsius? After 4 degrees Celsius, its volume actually starts to increase, and the density actually starts to go down, right? And at 0 degrees Celsius, again, we are seeing that it is not at the maximum density. It basically means that ice has got lesser density. If you are going to talk about the density, ice has less density than water, and that is the reason that ice floats on water. And the reason behind that is, although that is not in your course, but you must know it, the reason behind that, why we have got this anomaly over here. The reason is that we have got lots of space between those two hydrogen and oxygen molecule, right? That is H2O. So that actually, when we actually decrease the temperature further after 4 degrees Celsius, it actually starts to compact and the volume starts to actually increase. So the main reason lies behind the molecules, right? Next thing is, now we are going to actually talk about two or more important points. Water at 4 degrees Celsius, being the heaviest, settles at the bottom, while the lighter, colder layer forms on top. Consequently, in winter, the top layer of water freezes first, forming a protective layer of ice that insulates the underlying water from the cold, right? After that, since both ice and water are poor conductors of heat, this layer of ice effectively shields the aquatic life from the harsh winter and temperatures. Understanding these anomalous properties of water is crucial for appreciating its vital role in sustaining life, right? So this is actually everything that we need to know about the expansion of water after 4 degrees Celsius, right? Now let's talk about a very important topic, that is specific heat capacity. When we are going to talk about specific heat capacity, I would actually like to explain something over here, and that is, when you actually heat a certain body, right? So let's suppose that we have got a body over here, and the body is kept something like this. Let's suppose the mass of the body is m, right? Initially it is at temperature some T. So now what I am trying to say is that the amount of heat that we are going to give to this body, that is the amount of heat, is actually can be written as mc delta T. mc delta T. Now what do we really mean by this? By this we basically mean to say that the heat that is getting out of a body or which is getting absorbed by a body is directly proportional to the mass of the body, is directly proportional to the change in temperature of the body, and this constant that we have written over here, that is as C, this is actually known as specific heat of water. Oh, sorry, specific heat of any substance, specific heat capacity of any substance. Now what do we really mean by that? Let's read some definitions. When two materials initially at different temperatures comes into contact, heat flows from the warmer material to the colder material until both reaches the thermal equilibrium. Now this is very important. What do you mean by thermal equilibrium? We basically mean to say that let's suppose we have got a body over here and we have got another body over here, and we have actually connected these bodies, let's say through a conducting rod. We are going to talk about this in the next chapter again. Now heat, and we are going to also say that let's suppose the temperature is T1 over here and it is greater than temperature T2. So we are going to say that the heat is going to flow from the hotter body to the colder body. That's what we are saying, till they both are at the constant same temperature, that we are calling as thermal equilibrium, right? According to the law of conservation of energy, heat gained by a initially colder material equals to the heat lost by the initially warmer material, right? And we also discussed that the heat formula is going to be equals to mass times specific heat capacity times change in temperature. So now if you want to actually define what do we really mean by specific heat capacity for a body, we can actually define it something like this. We are going to use the formula. We are going to say that QC is actually equals to Q divided by M times delta T. This is very, very important to define this formula. Now we can say specific heat capacity is the heat. So let me write it over here. Yes, it is the heat required to raise the temperature by 1 degree Celsius of 1 kg mass. Is that correct? Well, this makes complete sense, because please understand over here that if I am talking about C equals to Q divided by M times delta T, so I am saying specific heat capacity will be actually equals to the heat required to raise the temperature by 1 degree Celsius of 1 kg material. Is that correct? So the SI unit of C will come out to be, we can easily see that the C has got the SI unit as heat is joules, joule per kg per degree Celsius. So this is the SI unit of specific heat capacity, right? So let's take some example for better understanding. Let's suppose that we have got two materials. And those two materials are, one has got a specific heat capacity of, let's consider water. I think it has 4200. I think, okay, let's just select any other material. Let's suppose that one of the material has got specific heat capacity as 100 joule per kg per degree Celsius, and another material has got specific heat capacity of 5 joules per kg per degree Celsius, right? And now I am saying to you that if I want to use these materials, I mean, in which cases I should use them. So you're going to say that, okay, so the first one actually requires 100 joules of energy. If you're going to take 1 kilogram of that material, 100 joules of energy will be required to raise the temperature by 1 degree Celsius. And for the second material, if you're going to take 1 kg of the material, you will just require 5 joules of energy. So in terms of energy efficiency, the second one is actually a better material. If you really want to change the temperature very quickly using very small amount of energy, so material 2 is actually quite good, right? So that's how we actually use it. When a material absorbs heat energy, its temperature increases. However, when equal masses of different substance receive same quantity of heat, their temperature rises differently. It means that they have got, if we are talking about different materials, they have got different specific heat capacity. So specific heat capacity is constant for a given material. So if someone says to you that we have got two bodies of same material, that means they will have same specific heat capacity, even if they have got different mass, any dimensions, right? So already we have talked about specific heat capacity formula. Specific heat capacity formula is nothing but del Q, that, or you can simply write it as Q, that is heat divided by M times delta T. Please remember the formula. In this formula, Q is actually the heat, also it can be also called as energy, same thing. M is mass and del T is change in temperature. Change in temperature. Moving on, now we are going to talk about change of state. In change of state, this is now something very, very important, and in the last class we actually talked about it. So if you have got a solid material, and let's just consider it as ice, if you are going to increase the temperature, what will happen is, how the things are going to work. If you are going to actually increase the temperature, what's going to happen over here is, the particles will move apart. That's what we call as expansion, right? And during this, temperature also rises, right? How this is actually happening, I'm going to also explain it to you. What we are basically saying is that, let's suppose that we have got an ice cube over here, we have got ice over here, and we are constantly giving some heat to it, some energy to it. So because of this energy, the temperature is rising, and because of increase in temperature, the expansion is taking place. This expansion will happen only up to a certain limit. After that, what will happen? The next step is going to be change of state. So during change of state, still the heat will be supplied, but now the temperature will be actually constant. This is very, very, very important, right? So that's what we actually say. When the water starts to boil, at that particular point, the state of the substance is actually water as well as vapor, right? Or if, let's say, if ice starts to melt, it melts at 0 degree Celsius, just above 0 degree Celsius, and the water freezes at 0 degree Celsius, isn't it? So that means at 0 degree Celsius, you could have either water or ice, or you could have a mixture of both, right? It depends on whether you are actually giving energy to the body or you are actually extracting energy out from it. Are you getting it? Now what we are trying to say is that, let's suppose you have got ice, you were actually giving energy to it, particles were moving apart, it was changing state. Now the change in state was something like, it was moving from ice to water. At change of state, it is at 0 degree Celsius and it is at 0 degree Celsius. So till the water is at till 100% of ice gets converted into water, the temperature will remain constant, and after that again temperature will start to increase, and now you can pretty much understand this concept, right? So from here till here, the amount of heat that is supplied is actually written as Q1. Are you getting it? And again, Q1 can be actually written as mass of ice times specific heat capacity of ice times change in temperature. Then after this point, that means at from, I'll choose another pen, from this point to this point, The temperature is not changing. That's why we are seeing a parallel line. And at this point, we have got ice and water. And the amount of energy that is required to completely change the ice to water is called as latent heat of fusion. All right. Although you are not going to require the formula for this, but still I'm going to explain it. Latent heat of fusion is actually given as m times L, where L is the latent heat of fusion, coefficient of latent heat of fusion. It is constant for a particular material. Then again, it will start to actually, the temperature will increase from 0 degree Celsius. So friends, this is actually 0 degree Celsius, and the boiling temperature is going to be 100 degree Celsius. Same thing is going to happen all over again, right? This amount of heat is required as latent heat of vaporization. Hopefully everything is clear till here. Moving on. Now let's talk about some of the questions related with this chapter. In which situation does the store of internal energy of the water increases? So it's quite easy. What do you mean by internal energy? We know that internal energy is the sum of energy of all the molecules of that matter, right? So if they are saying that internal energy of the water increases, it means that the temperature must increase. So water at 0 freezing to ice, if it is freezing to ice, that means the temperature is actually constant, right? It will be 0 degree Celsius. Internal energy won't change. Water being heated from 25 to 40 degree, this is the correct answer. Steam condensing on a window is actually not the correct. Water, B option is absolutely correct. The diagram shows the equipment used in an experiment on the heating of aluminium. The table gives the results for the experiment. The specific heat capacity of aluminium is 900 joule per kilogram per degree Celsius. What is the maximum possible temperature rise in the block? All right, so we have got mass, we have got voltmeter, ammeter, and we have got time. All right, so and we also have got specific heat capacity, right? So please try to understand what they are really trying to say to you. Over here, that we have got a power supply and we have got an heater. First of all, because of this electrical energy, heat energy will be generated. So we need to actually first talk about the heat energy. And heat energy will be found out using the formula for electrical energy, right? Now this is something that you need to actually know. Now we know that we can write the heat that is produced, we can rewrite that thing as VIT. And we know that voltage that's given is 12 times current, that is 5 ampere, times time, that is 300 seconds, which would basically mean the heat produced is 18,000 joules. Now if you want to find out the change in temperature, we are going to use that heat can be actually written as MC delta T. So change in temperature would be 18,000 divided by mass, that is 0.80, times specific heat capacity, that which was given as 900. Solving this, we are going to get 25. So 25 degrees Celsius is the correct answer. Let's move to the next one. Question 3 says a bimetallic strip is used to control the temperature of an electrical appliance. It is made up of two different metals fixed together. So we know what bimetallic strip is, right? Now that's why I was saying that completing some theoretical concepts is very important. These questions are going to be very easy now. The diagram shows the shape of the bimetallic strip before and after heating. So before they were quite linear, and after they have bent, and now I can clearly say that metal P has expanded more. It has expanded more, and this one has expanded less, right? So metal P expands more than the metal Q on. And just for an information, usually when we talk about bimetallic strip, this happens to be copper and this as iron. Moving on, a wooden wheel can be strengthened by putting a tight circle of iron around it, which action would make easier to fit the circle over the wood. Cooling the iron circle only, heating the iron circle, heating the wooden wheel and cooling the iron circle. Heating the wooden wheel but not heating, or so please see. Now the problem is that the iron circle is actually more than what we can say the wooden wheel, right? But we really want to we really what we want is we really want to actually fix them together. So what we are going to actually do is we are going to actually heat the iron circle, right? We are going to heat the iron circle so it will expand, and then we are going to fit the wooden wheel into it, and then we are going to let it cool. So the iron wheel will actually contract, and it will actually hold the wooden wheel tightly. That's how it will work. Obviously you don't want to actually heat the wooden material, right? For obvious reasons. Next question says a chef heats some water in a pan on a hot plate. The temperature of the water rises by 10 degrees Celsius in time t. She then puts the same volume of oil in an identical pan on the same hot plate. All right. The specific heat capacity of water is 2.5 times that of oil, and water is 1.1 times denser than oil. What is the time for the temperature of the oil to rise by 10 degrees Celsius? It's not that difficult. I'm going to explain it to you. First of all, you are using a hot plate. So what that hot plate is going to do is, again, that hot plate will generate heat from electrical energy, right? And if I'm not wrong, if they have talked about time, what I'm going to do is, instead of writing heat, I'm going to write heat as power into time. This is a very simple concept because power is actually rate at which energy is being liberated, right? So if I'm going to multiply power with time, I'm going to get what energy we are getting from the hot plate. Now let me just write it. Let's suppose the power of the hot plate is P, and initially when we were actually heating the water, the time was actually T. If I'm not wrong, the time was actually T, right? So P times T equals to what formula that I'm using over here is, I'll again write it for you. I'm just using that heat is actually equals to mass times specific heat capacity times change in temperature. This is the formula. All right. So instead of heat, I have written as power into time. Instead of mass, and by the way, I'm writing all of this thing for water right now. So instead of writing mass for water, I'm going to what I'm going to do is I'm going to actually write density of water times volume of water. I can write mass as density times volume times specific heat capacity of water times change in temperature was 10 degrees Celsius. Right now, for oil, power is same because you are using the same hot plate, but now the temperature now the time is going to be different. Density of oil times volume of oil times specific heat capacity of oil, and again we want to actually raise it to the same 10 degrees Celsius. Let's divide them. We have got two equations. Let's divide them. Power can be cancelled out, 10 can be cancelled out, and I know that they have written that specific heat capacity of water is 2.5 times that of oil. So I'm going to again rewrite this. By the way, this T is actually, let's just write it as T, this as T dash. Density of water is 1.1 times of oil. Volume of water is same, I believe that is same, right? Same volume of oil is being taken, and specific heat capacity is 2.5 times. So 2.5 times of C oil divided by rho oil V oil times C oil. So we can cancel out one by one all of these things. By the way, this is actually, again, this is going to be same, right? So that's what you're going to get. So the correct answer for this one is going to be It's going to be 0.36 times T. Obviously, you can do your calculation, but this is what we are going to get. T dash will come out to be 0.36 times of T. Hopefully, you have got it, right? Moving on to the next one. Thermal energy E is supplied to an object of mass m which does not change its state during the heating process. The temperature of the object rises by delta T. What is the specific heat? Very easy. Specific heat is going to be delta E divided by m times delta T. Option A, right? So this actually it came in 2023 paper of October-November series. 4 students are asked to state and explain the relative magnitudes of thermal expansion of solids and gases. Gases expand more than solids because the molecules in gas are in random motion. The first part is true. Gases expand more than solids because the attractive forces between molecules are much weaker in gases. Well, that is absolutely true. Solids does not expand more. The correct option is option B. Moving on. What happens when the temperature of the liquid rises? Well, mass does not change. Volume of the liquid actually increases, making the liquid less dense. Right? Hopefully everything's clear. These questions are quite simple. A scientist is determining the specific heat of vaporization of a liquid. He puts the liquid in a vacuum flask and heats it with a 100-watt heater. The mass of the liquid in the flask when it starts to boil is 300 gram. He continues to heat for further 12 minutes, after which the mass of the remaining liquid is 100 gram. What is the specific latent heat of vaporization of the liquid? Assuming that all the thermal energy of the heater is used to vaporize the liquid. All right. Now, please try to understand what we are trying to do over here. We are trying to say that we have got 300 gram of liquid, right, and it starts to boil, and the mass of the remaining liquid after some time is only 100 gram. What do you mean by this? It means that 200 gram of steam has been produced. 200 gram of steam has been produced, right? So actually we are going to use the formula of latent heat of vaporization over here. The formula was actually Q equals to M times L, right? Instead of Q, I'm going to use power, that is 100 watt times 12 minutes. So I'm going to convert it into seconds, times mass is actually 200 gram divided by 1000 times L that we actually want to find it out, right? So this will be actually 100 will actually 1000 times 12 times 60 divided by 2, that's going to be 6, and if I'm not wrong, this is going to be actually 360,000 joule per kg. So this is going to be the correct answer. Everything is an SI unit, right? Hopefully everything is clear with this question as well. Moving on. An ice cube of mass 12 gram at 0 degree Celsius absorbs thermal energy from surrounding at a rate of 3 joule per second. The specific latent heat of fusion is 330 joule per gram. How long will it take for the ice cube to melt? So we have got 12 grams, right? We have got 12 grams of ice cube, and we are saying that how much time will it take. So let's write again energy, as we are going to use the same formula Q equals to M into L. Instead of writing energy, I'm going to write power into time equals to M into L. So power is actually 3 joule per second multiplied by time equals to mass is actually 12 grams, and let me just use it as in grams because latent heat is also given in grams, right? So this is 12 grams times 330 joule per gram. So that's why I'm saying let's not convert the grams over here, right? So T will come out to be, this will become actually 4. So this will be 330 times 4, and that's around 1320 seconds. 1320 seconds. So please note one point that in the first part or in somewhere in the middle when we are talking about latent heat of fusion, I said that probably that will not come, but in some of the questions, especially in extended papers, we are seeing some of the questions. So please do note that whenever you are going to see latent heat of fusion or latent heat of vaporization, you are going to just use M into L. Don't use mc delta TO here, right? You can also remember it because during the change of state, temperature is not going to change. Temperature will remain constant, right? So we have completed this chapter as well. If you have any doubt, please write down your doubt in the comment section. We'll get back to you. I'm going to come back with another video pretty soon. Till then, take care. Thanks so much. Bye bye.